All right, so far we've talked about the concept of energy balances, but now let's put it into practice. And we could do that by working through this example problem from the book. All right, and so take the time to read the problem statement. But basically what's going on here is we have, this sort of piston cylinder system that I introduced earlier. All right, and so in this piston cylinder system, what we have is a gas that's underneath a piston. And the piston itself is fixed in place because there's like a clamp holding it so that it doesn't move. Right? Initially, the gas is at a temperature of 25 degrees Celsius. But then we take the entire piston cylinder system and we put it into boiling water while the clamp is still fixed into place. Because it's in boiling water, which is at 100 degrees C, even though the gas is at 25 degrees C, there ends up being a thermal difference between the surroundings and the system. And so as a result, there's heat that travels from the surroundings into our gas system, right? And this causes the gas itself to then jump up to a temperature of 100 degrees Celsius, and also a higher pressure as well. And so we let that happen for a while. The gas increases its temperature from 25 C to 100 degrees C. So that's the first step. The second step is that after the gas sits at that new temperature and pressure, the piston is then released, all right? And then the gas itself does 100 joules of work in moving the piston to expand to a new equilibrium position. All throughout the second stage of the process, the final gas temperature is still maintained at 100 degrees C, okay? And so for the process stages that are described in the problem statement, what you need to do is you need to write the energy balance equation for each stage of the process and then solve for all the unknown energy terms. All right? When analyzing this process, some assumptions that you can make is that, first of all, you need to take the gas to be the system. And you should also neglect any changes in the potential energy as the piston moves vertically. And also assume that the gas just behaves as an ideal gas. The problem statement also asks you to express all energies in joules. Okay? And so, with this problem statement in mind, what I want you to do now is I want you to pause the video and I want you to think about how you're going to draw out the sort of process flow diagram in each of these cases. In the process described in this problem statement, there's two distinct stages going on, right? In the first stage, the system is heated to 100 degrees C. Piston does not move, all right? In the second stage, the piston moves and the temp stays at 100 degrees C. Okay? All right, and so for each of these stages, we want to derive the energy balance and simplify it and solve for any unknown terms. Okay? All right, and so for the first stage, here's the sort of process flow diagram that I drew. Okay? And so what we have here on the left-hand side is this piston cylinder when we initially put it into the boiling hot water bath. Right? And so at a time 0, the temperature of the gas is 25 degrees C. But then, because the boiling water in the surroundings is at a much higher temperature, what ends up happening is we have heat traveling from the water into the gas system. Okay? All right? And then if we wait a long enough time, eventually that gas will heat up and reach a temperature of 100 degrees C. But all along, the piston is locked into place. Okay, so the piston is not moving. All right, and so for deriving the energy balance for this first stage of the process, what we should do is we should start with our energy balance equation for closed systems. Okay, so we have delta U plus delta EK plus delta EP, and that's equal to Q plus W. All right, so you should always start out by writing this energy balance equation. All right, now that we wrote the energy balance equation, the next thing we need to do is we need to eliminate any terms that are insignificant. All right, so let's go term by term, left to right. For the delta U term here, this is going to be significant. And that's because in the process, the temperature of our system is changing from 25 degrees C to 100 degrees C. Right? And so as the temperature increases, that means the molecular, atomic, and subatomic processes inside our system are also being affected. Those energies are also changing. Right? So we should expect to see a change in the internal energy. For the kinetic energy, our system is not accelerating, really. Like the gas is not moving anywhere. And at time 0 and at the final time, it's basically in the same place it was before. Okay? So we don't really need to consider any sort of change in kinetic energy. For the potential energy, the problem statement told us we could assume that the gas, or in fact, actually, we don't even need to consider that. What's going on here is the gas is not moving, right? And so there's no change in height for anything here. So also in this case, the potential energy is equal to 0. For the heat term, there is heat flow into the system from the surroundings, so the Q term is significant. For the work term, we don't have any change in the boundary size. There's no moving parts, and there's no electrical work. Right? So really, we can consider our work term to also be 0. And so after eliminating all the insignificant terms, what we get is that the change in our internal energy is going to be equal to the heat flow into our system as well. All right, and so at this point, we can now actually just calculate what the change in internal energy in our system is. All right, we said it's equal to heat. And the problem statement tells us that we have 2 kilocalories of heat going into the system. But it wants this in units of joules, so we just need to do a unit conversion. So 1 joule is equal to 2.39 e to the negative 4 kilocalories. And so what we get is that the change in internal energy in our system is 8,370 joules. All right? So that's the answer for the first stage of the process. Let's now move on to the second stage of the process, which deals with the part where the piston is allowed to move and the temperature of the system stays at 100 degrees Celsius. And so here's the process flow diagram I drew for stage 2. Okay? And so what we have is, at the initial state, in stage 2, the gas and the water temperature are both at 100 degrees C, and the gas system has some sort of size here. Then the piston is released, and we wait a long time, and this allows the gas to expand, right? And so when the gas expands, the gas is now doing work on the system, okay? And so let me draw it in green here. Nope, no, that's not green. This is green. Okay, and so the system expands, and this causes the system boundary to get bigger. Right? And in order to get bigger, the gas has to expend work against the piston. It takes effort in order to push against the piston and expand the system. Okay? So it takes effort, i.e. work, to push against piston. Okay? And so qualitatively, that's what's going on in here. But now let's be quantitative, and let's actually calculate, any sort of energy that's going on here. Okay? And so, or any sort of energy transfer that's going on into the system. All right. To do that, let's start with our energy balance equation for closed systems. delta U plus delta EK plus delta E, or delta EP, I guess I wrote there, equals Q plus W. And just to be consistent, let me switch K and P. All right, and so in our energy balance, let's go term by term to see if there's any terms that we could cancel out. All right, so the first term we'll look at is the change in internal energy. All right, and so let's think about what's going on here. The gas in our system stays at 100 degrees C. Right? Even though it's expanding, it stays at that same temperature. The problem statement, it told us to assume that we have an ideal gas. And for ideal gases, basically what that means is that, the internal energy of the system is directly related with the temperature of the system. And if the temperature is not changing, and there's no phase changes, and there's no reactions, and really there's no any information that tells us that the pressure is changing too much, what that tells us is that we could assume that our change in internal energy of our system is very small. That's basically equal to 0. So we could cancel out this delta U term. For kinetic energy, our system's not accelerating, so we'll say that's 0. For the potential energy, the problem statement told us we could basically ignore the raise in height of the expansion of the gas and its effect on potential energy. Basically, the center of the mass of the gas is not changing that much, even though it's expanding. And so that will allow us to cancel out the potential energy term. All right. As I mentioned before, in order for the system to expand, it needs to do work. So our W term is still there. For the heat term, our system, our gas, is not insulated, right? So we can't really say it's an adiabatic system. So we can't immediately say that Q is equal to 0. Now, the temperature of the system and the surroundings are the same, but for this energy balance, I want to point out that that doesn't necessarily mean that Q is going to be equal to 0. All right, and so in order to show that to you, I actually want to go through with the energy balance. Okay, and so what we have here in our energy balance is that Q plus W is on the right-hand side, and on the left-hand side, what we have is that all of that is equal to 0. All right, and so if we rewrite this, what we have is 0 is equal to Q plus W, and the problem statement told us that the system does 100 joules of work on the piston. All right, and since the work is going from the system to the surroundings, that means that our work term is actually going to be negative. Okay, and so if we rearrange this, what we end up getting is that Q is equal to 100 joules. All right. Okay, and so this is the result that we get. All right, this is what the math tells us. But physically, does this result make sense to you? Okay, why does heat have to go into the system? And so let me get my red out. Why does heat have to go into the system? Right, in this case. To understand why the Q term here is positive and not equal to 0, we need to think about, what's going on microscopically, right? And so in our system, remember, we have gas molecules that are bouncing all around. And temperature inherently describes, the speed of these gas molecules, the energy that they have. Right? In order to expand, the gas molecules have to do work in order to push the piston up. Right? And so from the work, these gas molecules are losing energy in order to push the piston up. All right? And so if energy is being lost in order to expand the system, if we want to keep the gas molecules at the same temperature, we need some sort of input energy in in order to get them back to that same energy level. All right? And so that energy transfer that they need in order to get back to 100 degrees C comes from the water bath. Right? And so in the end, in order to get back to that temperature of 100 degrees C, or to stay at that temperature of 100 degrees C, because energy is leaving the gas molecules in the form of work, there has to be an equal but opposite energy transfer coming from heat. Okay? And so, in other words, heat needs to go into the system to maintain T is equal to 100 degrees C.